Hello everyone. Welcome to another episode of Deep Dive Knowledge Talk. It's great to engage in this important discussion about wastewater treatment plants and their management. To set the stage, could you elaborate on the challenges faced in wastewater treatment operations that make the integration of multi-source and multimodal data particularly crucial?
Wastewater treatment plants are like busy kitchens that handle a lot of different ingredients, but instead of cooking food, they are cleaning water. The challenge here is that this kitchen doesn't always work in a straight line. Sometimes, the ingredients or data come in at different times from different sources and may not be very reliable or accurate. Imagine trying to bake a cake, but you only get some of the ingredients at a time, and some of them are stale or not right for the recipe. This makes it really tricky to know how to make the cake come out perfectly. Similarly, in wastewater treatment, the data about water quality may only arrive once in a while, and other measurements could be out of sync with those or might not be trustworthy. This complexity means that simply using the data collected is not enough. We need to use a special method that can mix all these different sources of information together, just like a chef would combine various ingredients to create a delicious dish. This is where multi-source and multimodal data fusion comes into play. It helps us gather all the pieces of information, despite their differences, and use them to make better decisions for cleaning the wastewater efficiently and effectively. So, the integration of this data is crucial, as it allows plant operators to understand better what is happening in their kitchen and ensure that the water being cleaned meets safety standards before it's released back into the environment.
That's a vivid analogy to illustrate the complexities of managing data in wastewater treatment plants. Can you delve deeper into how specific methodologies such as Bayesian fusion are used to address these challenges? What makes Bayesian fusion particularly effective in combining diverse data sources for improved predictions?
Bayesian fusion is like being a wise chef who knows how to make the best dish by combining the flavors from different ingredients, but with a special twist. The chef pays close attention to how reliable each ingredient is. In wastewater treatment, we often receive data from various sources like sensors or images, but some of this data may not be very trustworthy or can vary in quality. Instead of simply mixing together all the data, Bayesian fusion focuses on the predictions made by individual models built from each data source. Think of it as each ingredient giving its own recommendation on how the dish should taste. Some ingredients might be very fresh and flavorful, while others could be a bit stale. The clever part of Bayesian fusion is that it takes into account the uncertainty of each single source model. If a certain ingredient or data source is known to be less reliable, its recommendation gets less weight in the final decision about how to prepare the dish. Conversely, if another source is very reliable, its prediction has a bigger impact on the final outcome. This method helps improve predictions in wastewater treatment because it balances the strengths and weaknesses of each data source. By considering their uncertainties, Bayesian fusion can provide a more accurate and reliable estimate of the parameters we care about, such as toxin levels in the water. This approach ultimately helps in making better decisions for managing the wastewater treatment process effectively.
That's an excellent explanation of how Bayesian fusion operates. Could you share more about the specific results achieved through this methodology in the context of the case study? How did Bayesian fusion compare to other modeling approaches in terms of accuracy, stability, and flexibility for predicting toxin levels in the effluent stream?
In the context of the case study, Bayesian fusion proved to be a standout method for predicting toxin levels in the wastewater treatment plant effluent stream. When compared to other modeling approaches, such as the concatenated method, Bayesian fusion consistently showed better performance. To break it down, think of Bayesian fusion as a skilled conductor leading an orchestra, where each musician, data source, plays their part. The conductor knows which instruments are playing well and which might need a little more attention. This ability to weigh the contributions based on reliability led to the best results in terms of accuracy and stability. Specifically, Bayesian fusion produced the lowest prediction errors when tested under independent conditions. This means it was more accurate in predicting how much toxin was in the water. It also handled the data more robustly, especially when some sources of information were missing. Unlike the concatenated method, which struggled without complete data and required complicated steps to fill in gaps, Bayesian fusion could still provide useful estimates as long as at least one source was available. Furthermore, the flexibility of Bayesian fusion allowed it to monitor toxin levels daily, which is crucial for ensuring safety and efficient use of chemicals during the treatment process. This regularity helps maintain toxin levels below compliance limits, making the overall operation smoother and more effective. In summary, Bayesian fusion not only outperformed its peers in accuracy, but also provided stability and flexibility, making it an ideal choice for managing the complex and varied data from a wastewater treatment plant.
It's fascinating to see how Bayesian fusion excels in this context. Could you explain the nested cross-validation method used in the study? How did this technique contribute to handling the time series nature of the data and ensure robust model evaluation?
The nested cross-validation method used in the study is like a double-check system for ensuring that the predictions about toxin levels in the wastewater treatment plant are as accurate as possible. To understand this better, think of it as a school preparing students for a big exam. The school wants to make sure that the students are not only ready for the test, but also capable of performing well in different situations. In this case study, the time series nature of the data means that the data points are collected over time, just like how students take tests periodically, instead of just using a single data set to train the model and another to test it. Nested cross-validation divides the data into different parts multiple times. First, it runs through the data to train the model, and then it tests that model on separate data. This process can happen repeatedly, helping to fine-tune the model and ensure that it performs well not just on one set of data, but across various situations. By using this method, the researchers were able to evaluate the models more robustly. They could see how well the model predicted toxin levels at different times and under different conditions, so they could be more confident in its reliability. This thorough check helped ensure that the models would not just memorize the data they were trained on, but could generalize their predictions to new, unseen data. Overall, nested cross-validation contributes significantly by providing a rigorous way to assess how well the models work over time, which is essential when managing the dynamic and changing conditions at a wastewater treatment plant.
That analogy really illustrates the importance of nested cross-validation in ensuring model reliability. To wrap up our discussion, could you summarize the main contributions of this study to the field of wastewater treatment plant management? How do the findings regarding data fusion and modeling approaches potentially impact future practices in this area?
The main contributions of this study to the management of wastewater treatment plants revolve around the innovative use of data fusion and advanced modeling techniques. By exploring multi-source methodologies like Bayesian fusion and a concatenated approach, the study provides valuable insights into how to efficiently integrate diverse data from various sources, which is crucial for effectively predicting toxin levels in treated water. One significant finding is that Bayesian fusion outperformed other methods in terms of accuracy and stability in predictions. This means that wastewater treatment facilities can rely on it to make better informed decisions regarding the management of toxins, ensuring they meet governmental compliance levels and protect ecosystems from harmful pollutants. Furthermore, the ability of Bayesian fusion to handle missing data without complicated steps is particularly beneficial in real-world scenarios, where data might not always be complete. The study also highlights the importance of variable selection, which can enhance the performance of modeling approaches, making them more reliable. This practical advice can inform future methodologies and operational practices in the field. In summary, the findings regarding data fusion and modeling approaches have the potential to significantly improve future practices in wastewater treatment. By adopting these advanced techniques, facilities can enhance their operational efficiency, ensure environmental compliance, and ultimately contribute to better water quality management. This sets a foundation for further exploration and development of flexible data-driven solutions tailored to the specific needs of wastewater treatment operations.
Thank you all for joining us today. In this discussion, we've explored the challenges of managing complex data in wastewater treatment and the effectiveness of Bayesian fusion as a solution. We've learned that Bayesian fusion integrates diverse data sources and considers uncertainties to enhance predictions, outperforming other approaches in accuracy and stability, especially when data is incomplete. nested cross-validation, ensures robust model evaluation and generalization. These findings contribute to improved toxin management, optimized treatment operations, and environmental protection. We encourage you to explore these concepts further and apply them in your own work. Thank you again for your participation.